Schwarzschild Geometry. What is actually our aim? Okay. So our aim is let's look at the Newtonian perspective. So you are having some mass, okay? So it produces gravity, because mass, and you ask what? Let's have an observer who is in the free fall. Okay, what is the trajectory of this very observer? Let's say some another observer is watching this free fall. What should be the trajectory? It should be it's under gravity. It's a free fall under gravity of this very object. From the Newtonian perspective, you can see the trajectory will be given by the Newton's equation. Okay, what is the mass of this very object? Let's say it is mass, g is the Newton's constant, and this is r square. Okay, but the point is here, this is the double derivative. Look here. So it is the double derivative of this. What this is? It's a coordinate. Sorry, it is the radial distance, or what? Is it radial distance? This r? Sorry. So what about this r? Forget about this r. What about this r? This r is actually the distance of separation from the center to this very object. So it is actually a coordinate distance between the two. Got it? Okay. Now what about this thing? So we are figuring out this r in terms of this t. What is the function of this r in terms of t and as a function of this mass? So although if I fix this mass, only r will change when it is under the free fall. So it is simple, the free fall equation. Now the one important point is that, so here t is a universal kind of quantity. It's a universal clock exists there, such that the time for this observer at this point and at this point they are the same. Is it true? Because in the Newtonian mechanics, time is absolute. Yes, sir. And the interaction take place at the infinite velocity. Got it? In that sense, the time is absolute for everything. So this will be the trajectory. Okay, and this r will be the distance of separation between the two bodies. The test particle, what we call the observer, okay, and the center of this mass producing the gravity. Got it? So this should be it should be now clear what these things mean. But here now, if we are having the Schwarzschild geometry, the line element is like this thing. So what is our line element? 1 minus twice mu by r, okay, c square dt square plus, then you are having 1 minus 2 mu by r minus 1 dr2 plus r square d theta square plus sine square theta d phi square. For a spherically, symmetric object, this is a kind of geometry outside it. Okay. Now in this very geometry, now you are having a space-time arising here. In this very geometry, I am trying to figure out what could be the trajectory of a particle, or what could be the trajectory of the light. Because we know now the gravity bends the light. Gravity has an effect on the mass as well as massive particles as well as the massless particles. Clear? So we are trying to figure out those kind of geodesics. What are the equations of motions describing those geodesics? Those geodesics we call, if it is the light, we call it as a null geodesic, and if it is some massive particle, we call it as a time-life geodesic. So our aim is actually to look at general formulas for time-life and null geodesic. Now outside this very objective, you don't have this Newton's law. Okay? We need to figure out what kind of equation of motion will be governing for a particle under free fall. Okay? So instead of putting the particle here, I will put here. It is actually the free fall. So you want to switch each free fall, okay? So because it's a cipher, so this is also the free fall. We will do it in this way. Clear? Have you got now the idea what we are trying to figure out? Yeah? Okay, so let's consider a particle. First, so let's consider some Lagrangian for a free particle. Okay, in this curved space-time, so it will be g mu nu x dot mu x dot mu. So this is how we will arrive at actually the equations of motion. So geodesics, I know I can figure out them from simply the Euler equations. So you got समझ? Last time I have told you. So if you know the Lagrangian, you can figure out what the Euler equations of motion. Those will give you actually the geodesics. Okay. So now how many coordinates are here? Tell me. You are having t, r, theta, and phi. So that means this equation will be having. We'll be having how many equations at hand? So for each variable, I will be having an equation. The 4 equations I will be having at hand. An equation corresponding to this t, okay, an equation corresponding to this r, theta, and phi. Okay, so let's look at this thing. So what is our g mu nu? So here, what is our g mu nu? It's actually the diagonal of this very objective. So it is something minus 1 twice mu by r. Okay, then you are having 1 minus twice mu by r raised to minus 1. Then you are having r square. Then you are r square sine square theta. By the way, if anybody is not able to, at the first instant able to figure out these matrix and so on, so I will tell you frankly, when I was doing the GR at your time, it was very difficult to me to comprehend. Okay, I was not actually able to write a matrix for a cylindrical in cylindrical coordinates. Okay, so don't be afraid. So you are not able to do it. So just be relaxed. You'll with passage of time you will actually understand things. Okay, but you have to constantly drive yourself through these equations. Okay, then you can understand it. Okay, so let's write this Lagrangian. And it was actually very difficult for me to understand GR at the very first instant. Okay, really, I am saying really, I was not able to comprehend what is happening. So, but over a period of time, I gained the experience, and it's now easy. Okay, so just be relaxed, huh? So, okay. यहाँ छो तो अगर तो 11th या 12th में जैसे अक्सर. So what is our Lagrangian? So g mu nu. So it will be minus 1 minus twice mu by r. So what will the So what will be this thing? So x dot 0. So g 0 0 0 0. Okay. So what is that? So it is c t dot. So it will be c square t dot square. Okay. What is the derivative with respect to here? It is with respect to some affine parameter. Okay. So this x dot is simply dx by d sigma, and sigma is some affine parameter. Okay. So you think like, so sigma is like a proper time. Okay. Affine parameter. If you are not able to understand, look here. So look at the geodesic equation what we have at hand. So let me define it this way. Suppose this is your geodesic equation. If you remember, dui by d tau plus some I j k uj mu k is equal to 0. Okay. So this is valid for any kind of parameter. So if I change now my parameter to some another parameter, the set of parameters f of lambda, I can make this invariant. This very object can be made invariant under this kind of parameter transformation. If you are having this equation invariant under the set of transformation of the parameters, those parameters we call as the affine parameters. Or in other words, this equation is invariant under a linear transformation of this parameter. Look, you take one of the parameters is your tau, that is proper time. Clear? It's not necessarily to choose proper time. You can choose another kind of parameter. Let's call it some gamma. Or you can choose, somebody can choose another kind of parameter. So that means you are having a family of parameters at hand. One of the member of that family is your tau, proper time. Clear? Okay, so now if I want this equation to remain invariant under this kind of transformation, change in parameters. Okay, so it will be something, let's say dui by d lambda plus some gamma I j k u j u k, okay, is equal to, so there will be some, okay, let's assume it is equal to 0. Let's assume for the time being. If this happens, then we call these lambdas as the affine parameters. So if you change this kind of formula just by the chain rule here, let's say if I look at the chain rule, like what will be the chain rule? So you are having dui by, let's say d lambda, then d lambda by d tau, and similarly you will get a function here. Okay, so on the right hand side, instead of the 0, you will get a derivative of f, for example. For example, you will get a derivative of f, for example, so with respect to tau. Okay. Now, since you are having an additional term on the right hand side instead of the 0, that means it does not look like this equation. Okay. You need to put this right hand equal to 0. So that means if I put this derivative equal to 0, so it means that f must be what? Some linear function of this parameter tau. समझ आया? That's why we call sometimes these affine parameters as linear parameters, or the transformations. There exists a linear transformation between the set of the parameters. समझ आया? तो यहाँ क्या समझ? Or in other words, a simple way, an affine parameter means, so you draw a tangent to the curve. If you parameterize curve in such a way that the tangent moves along the direction of the motion itself, that it moves along the curve itself, like this thing. Suppose if you are having, let's say, curve, so tangent here is like this thing. What is the tangent here? So they are in the not same direction. If I am putting a tangent as an autoparalleler, I am parallel to itself throughout the trajectory, then I can say my trajectory is defined by, parameterized by an affine parameter. समझ आओ? Think of a light. Light ray is like this thing. What is the tangent direction? So it is autoparallel to it. Yeah? So every point it is along the curve itself. So समझ आओ? Got it? वो आओ समझ affine parameter क्या हुआ? Huh? Affine parameter is such that, okay, a curve is parameterized by some affine parameter. It means the tangent to a curve at every point is autoparallel to itself. Got it? Okay. So, okay, forget about whatsoever. So you can say this is some parameter with respect to, we are doing differentiation, okay? But these are linear parameters. They have the physical significance, let's assume. Huh? Okay, so what would be the next thing? Next term, G00. So now we are having G11. What is G11? It's 1 minus 2x mu by r raised power minus 1. So it will be dr2 plus G22. So that is r square. Then it will be d theta square because it is r dot square. Then I am having theta dot square. Then what I am having? R square sine square theta. Then phi dot square. So this is our Lagrangian. Now if you look at the Lagrangian carefully, so it depends on r, it depends on theta. Is it? So look here, this Lagrangian depends on what? R, theta, the variables itself. So what are the variables? Our coordinate system is like p, r, theta and phi. Samajh? Now tell me, does t arise explicitly in this Lagrangian? There is a t, but that is t dot. It's a derivative of the time. Samajh? And there is actually a phi, but it's phi dot. It is a derivative. Huh? So it's like this thing. It's a phi dot square. Okay? So there is r and there is what? Theta. Samajh? So Lagrangian depends explicitly on r and theta. Okay? But if it does not depend on a given coordinate, let's say Lagrangian does not depend on t and phi, then what we call those variables? Ignorable variables. Okay? So that means, so t and phi are what? Ignorable coordinates. Samajh? So when you are having an ignorable coordinate in a given Lagrangian, it means the conjugate momentum corresponding to those variables remain conserved. So it means a conjugate momentum corresponding to this phi should be conserved and a conjugate momentum corresponding to this t should be conserved. And we need to figure out what exactly those are. We need to interpret these things. Okay? So let's first proceed. This was a simple, observation here. Okay. So let's try to now figure out the equations of motion. Okay. So what is our Euler-Lagrange equation? V by d sigma, okay, partial L by partial. So let me write x dot I minus partial L by partial xi, that's equal to. Is it true? So now let's take I equal to 0. So what that is? V by d sigma partial L by partial x dot 0 minus partial L by partial 0 x 0. So that's equal to 0, or in other words I am having this very equation, d sigma partial L by partial t dot. It will be c t dot. This is c t here. C you can take out, so it will be simply partial t equal to 0. Clear? समझ आओ? Okay, so now let's derive. So let's derive equation. Angasa? Derive. So what is our partial L by partial t? First tell me. So that's equal to 0 because there is no dependence on t. Teacher? Okay, so now question, sir? Okay. So what is our partial L by partial t dot? Tell me. So these things do not depend on t dot, that depends on t dot. So what that is equal to? Minus 1 minus twice mu by r. So let's write this way. So it is c square twice t dot. Clear? So, or in other words, so what is the equation? D by d sigma r, this very objective, minus 1 minus twice mu by r, okay, twice c square t dot, this is equal to 0. Clear? Okay, so which gives me, so this is an equation, this is a geodesic equation governing the time coordinate. Samasha, governing the t variable or the zeroth equation from this. Okay. Okay. So now let's. So I will take it out. So it is d by d sigma, like this thing, 1 minus twice mu by r, because now r depends on the parameter as well. Huh? So these are not the distance between the observer and the center of center of the this spherical body. Huh? This is actually the radial coordinate. Huh? So that is the difference between the Newtonian mechanics here. Samajh aa? So this is not the coordinate distance. Huh? So this r depends on sigma as well because it will depend upon how you choose the parameters of a given curve, of a given geodesic. So that's why you cannot take this object out of this differentiation. Okay, so it will be t dot is equal to 0. समझ आया? So now if you differentiate it, so sorry, if you integrate it on both sides, what you will get? So it means this object has to be constant. समझ आया? So which implies therefore 1 minus twice mu by r, okay, E dot, it is a constant, K is a constant. Okay, so let's call this equation as equation 1. So we have got first equation corresponding to the K, corresponding to the T. Clear? Okay. Now we need to interpret. We need to figure out what exactly this constant K is and what is the interpretation for this K. Clear? So that we'll do later on. First we'll try to derive the equations. Okay. So now let's take another thing. Everybody has written it? Okay, so let me write it here. So let's write later on. Okay, so let's take now I is equal to 1. So that means it is actually R equation. Huh? Clear? Okay, so partial L by partial R. So look here, this contains also a factor of what? R. This contains a factor of R. This contains a factor of R. This contains a factor of R. Okay, can you do it? Or shall I do it? So, okay, sir. So, so you are having minus, then you are having minus twice mu. Okay, what is the differentiation of 1 by R? It's minus 1 by R square. Okay, then you are having C square T dot square. Clear? Then you are having, okay, minus 1 will come down from here. Okay, so you are having minus 1 minus twice mu by r, then it will be minus 2 here. Okay, then you are having minus twice mu. Okay, then you are having minus 1 by r square. Okay, so r dot square. So then you are having plus twice r theta dot square plus twice r sine square theta. Okay, phi dot square. Okay, so now let's substitute it in the equation. Okay, now you are having a differentiation. Okay, so let's write this thing. So let me write this thing, d by d sigma partial L by partial r dot. So what that is? So 2 will come out. So it is d by d sigma r 1 minus twice mu by r and r dot. So how much is that? So that is equal to, okay, so now let's differentiate it. So it is twice, okay, differentiation. So it's minus twice mu. So it will be now 1 by minus 1 by r square. Then the differentiation of r. So it is dr by d sigma, and r dot is there. Now then there will be another term because I am using the product rule. So it is 1 minus twice mu by r. Okay. So r dot will be r double dot. So this object is actually r dot because it is the differentiation of r with respect to sigma. Everybody? Okay. So look here. So this is this object is this thing. So you use now the product. Oh, sorry. There is a wrong. There is an error. Okay. So there is a minus 1. So use the product rule. So it is minus coming down. So minus 1, 1 minus twice mu by r. Okay. So raise for minus 2. Then there will be a differentiation of this thing. So it is minus twice mu multiplied by minus 1 by r square, and dr by d sigma, that will be r dot. And then you are having r dot with this thing. Okay. Then plus 1 minus twice mu. Yeah, there is a 2 factor outsider. You need to take care of that 2 factor. Minus 2. So it's 2 by r raised for minus 1. Then you are having r double. Okay. So now plug in every term here. Okay. So use all the terms together. So you will get this kind of equation. Okay, you need to look properly. So it is, so which implies therefore you are having 1 minus twice mu by r raised to power minus 1 r double dot plus mu square c square by r square t dot square. Okay, yes, this is the t dot square twice mu by, because there is a 2 everywhere, that 2 you can take out. Okay, so then you are having minus mu by r square 1 minus twice mu by r raised to power minus 2 r dot square. Okay, then you are having minus r theta dot square plus sine square theta phi dot square is equal to 0. So call this as equation. Okay. Similarly, we can have theta and phi equation. So let me write theta and phi equation directly. Okay. So what you need now? So you need theta equation. Okay, so what is theta equation? Theta equation will be d by d sigma partial L by partial theta dot minus partial L by partial theta is equal to 0. So this yields this kind of equation, theta double dot. Okay, where is the theta? So rest will not contribute, only these will contribute. Samajh aaga? So it will be something theta double dot plus 2 by r dot theta dot minus sine theta cos theta phi dot is equal to 0. So let's call this as equation 3rd, and we are having now the last equation, d by d sigma partial L by partial phi dot minus partial L by partial phi is equal to 0. So this gives me like, so phi is contained here only, is it? So only the phi dot, there is no phi. So what is the differentiation? So it is simply r square sine square. Okay, so it will be like this thing. D by d sigma r. What is partial L by partial phi dot? It is simply r square sine square theta phi. So it will be twice phi dot, because partial L by partial this is, so it is twice phi dot, that is equal to 0. So let's integrate it out. So it gives me simply r square sine square theta phi dot is equal to some constant. H is a constant. Okay, so let's call this as equation 4. We need to interpret k and h, so that we'll do in a moment. Okay. Clear? So these are all geodesic equations, and they are valid for both time-like as well as null geodesic, because we have not assumed any kind of condition whether my geodesic is null-like or time-like. Clear? So samajh aaya? Okay. So that means these are valid everywhere. So now let's look, since we are looking at a spherically symmetric body. Okay. So an object which is spherically symmetric, the gravitational field is spherically symmetric outside that. Okay. The point is that means I can, to simplify my calculation, I can choose only one of the planes, or I can choose only one of the points. Samajh, what are the points described here? Let's say a point on a surface of the sphere, it is described by theta and phi. So that means at my choice, so you cannot choose a t, you cannot choose a r, because wherever you go, you will be at a distance of r from the body, is it? And wherever you will go, you will be attached with a time. But what is at disposal, which you can fix? You can fix an angle at which there is a free fall. Okay, both theta and phi. Samajh? So let's choose. Let's simplify our this calculation. Because of spherical symmetry, we will choose theta equal to pi by 2 plane. Okay. So let's choose this plane. So it means we are in the equatorial plane. Theta is equal to pi by 2 is where? It is equator. So we are actually in the sphere. Let's say this is a spherical body. So we are actually here. So in this way we are choosing a free fall in this very plane. So got it? So we can think only of this very plane now at hand. So what is fixed now? So when theta is equal to pi by 2, theta is fixed. Okay? So that means I don't need to take this very equation into account. So samajh? And what will happen to this very equation? So let's take, since theta is fixed, so this will be 1, is it? So I'll be having only 3 equations at hand. One is r square phi dot like this thing, another is like this thing, and the first one. Okay? Now look at the Lagrangian itself. When I fix, let's say theta, okay, so this term will not be there. So you can fix, let's say, phi as well. Let me fix the points on the sphere. Let me fix a plane such that theta and phi are fixed. Clear? So that means the metric what I can choose, I can ignore these things. I can only play with what? T and r coordinate. Let's say you start with a line element which contains all the 4 quantities, t, r and theta and phi. Clear? Now I will fix my plane which has what? Theta and phi fixed. Clear? So what are remaining? So whenever you do the analysis, you can only play with t and r. So you don't need to consider theta, the angular portion. Because you are in the fixed plane. Got it? And that is a very convenient choice to do things. Okay? Okay. So let's fix these things. So that means when I fix this thing, what are these r equations? So in this plane, so we'll be now able to, so let's write. So in this plane, so let me write the first equation. So what is that? 1 minus twice mu by r, okay, t dot, that's equal to e. So is it correct?
Yes, sir.
Huh? So what will be the now second equation? So let's look at this thing. Okay, so it is 1 minus twice mu by r, okay, raised for minus 1, r double dot, plus mu square c square by r square t dot square, okay, minus mu by r square 1 minus twice mu by r raised power minus 2 r dot square, okay. Theta is fixed, so you will be having only minus r, sine square theta will be 1, so r phi dot square is equal to 0. And there will be no theta equation because theta is fixed, okay. So the third equation will be hanging at hand, so it will be r square phi dot is equal to, okay, clear? Now let's try to interpret these equations. Let's interpret the k constant and the h constant. So it's not 0, it is h. Oh, sorry, this is 0. The h is here. Okay. Clear? Okay, so let's try to interpret. So we will interpret these constants k and h. Okay, first let's take. So what is the momentum corresponding to phi variable? Since theta, okay, this p and phi are ignorable. So it means the conjugate momentum. So what is the conjugate momentum? Let's call that as L phi. So what will be that? Angular momentum. So the angular phi, you know, the phi is an angle. So the angular momentum about related to this phi will be what? A conserved quantity. Now let's look at that very thing. So okay, so what is our this L phi? So it will be simply partial L by partial phi dot. Okay, so how much is that? That's simply equal to r square phi dot. Isha, is it true? No, you start with the Lagrangian, and in the Lagrangian at the end term is what? R square sine square theta phi dot square. Okay, r square sine square theta, because we are in actually which plane? Equatorial plane. That's why I have not taken sine square theta. So much, that is the simplest of the case. So what is the angular momentum? So what is L r square phi dot? So what is that equal to? H. So what is the interpretation of this H? This is the z component of the angular momentum in the usual sense, but it is the phi component of the angular momentum. Okay. So that means this has the interpretation of what? Angular momentum related to phi. Okay. And it is conserved. Got it? So that means, so you can put this H by L, whatever is the angular momentum. Okay. So now let's look at the another case. So let's look at this T. Now tell me, when the time is okay, think of the Newtonian mechanics. When you are having time as homogeneous, that means there is a time translation of a Lagrangian. What is the quantity that is conserved? Energy. So when you are having a space, translation in the space, okay, so if you are having invariance and translation in space, then the linear momentum is conserved. Now if you are having a time translation invariance, so it means energy is conserved. So it means this T should give me what? The ignorable coordinate. This T ignorable coordinate should give me the energy. Okay, so we need to check whether it is really the conservation of the energy or not. Okay, and if you see whatever equation you have encountered in mechanics or wherever, our equation is always the equation which solves the energy equation. Look at the Schrodinger equation. So which equation is the which equation gives you the energy of the particle? It is the radial part of the Schrodinger equation. Clear? So if you follow the Newtonian mechanics for an arbitrary potential, so it will be always the radial part of that very equation which gives you the energy. So that means this equation 2, which is the radial equation, this describes what? The energy of the particle. So sure? Got it? Okay. So let's look at this ignorable coordinate. So let's calculate this partial L by partial T dot. So let's for the time being call it as E. And I don't know what E is. Okay? So what is partial L by partial T dot? So it is 1 minus twice mu by R. So it is 2 times T dot. Isha? So Chana E? This is the case? Okay. Okay, so is this energy? Okay, what is T dot? Okay. First let's check. What is our T dot? Let's take the proper time. So it is dt by deta. So you can choose now sigma equal to tau. So what is this thing? So it's actually gamma. Yaad hai? Root of 1 minus v square by c square. You sure? Or this we have been deriving all the time. Okay? So that means T dot is gamma. Okay. So you are having this E is equal to now 2 into 1 minus twice mu by R into gamma. So now let's interpret it a little bit more, because we need to fix something. So let's say you are having the observer is at infinity. So that means we are far away from the source. Samajh? Clear? So what this will be? Sorry, we are having 2 is a problem.
Sir, equation first with 2 नहीं है, वो T dot है.
Huh?
T dot.
Somewhere. Sorry, I can put this as 2e because of this factor 2e. 2e is something e prime, okay? So that I can cancel this 2. So much, huh? So I can simply write it down like this. So this is gamma. Okay. So now let's take you are having the observer at infinity. So much, huh? What does that mean? I am now at this. Okay. So what should be the interpretation of this t now? So when the observer is at infinity, this should be now the coordinate time of the observer. Samajh? And this t always represents the coordinate time, and you are having this as the proper time. Samajh? So what will happen to this E now? So what it where it goes? So it's simply gamma. Samajh? So now if I multiply this by mc square, gamma divided by mc square. Can I do it? Can I do it? Samajh? Now tell me what this object is. This is actually the energy of the particle. So we should actually put the constant k. Okay, so what's up? So this is the energy, is it? Is this the energy of a relativist particle? So let's call that energy as E naught. So what that is? So now if you see, that means this E has actually the interpretation of the energy. Although it is not purely energy, it is actually energy per unit the rest mass. So this is actually the energy of the particle, and this is what you are dividing it by the rest mass of that very particle. So then what is the interpretation of this very k? Now you got this. You got now this represents the energy. So that means your t coordinate gives us the conservation of the energy. Got it? Okay. So now what is the interpretation of this k? So k is simply equal to, since k is as E. If you see, k is simply as E. So in other words, I can write my k as E naught by mc square. Okay, so let's forget about this E naught. Call this as simply E. Okay. So in other words, our energy is equal to k mc square. Samajh? Got it? So this is the interpretation of our these constants k and h. Clear? If anybody is having problem. Anybody having the problem? Is it clear? Okay, good. So let's move ahead. Just a few minutes. So till now, this is valid for equally valid for time-like as well as null geodesics. Okay, so we'll look at the trajectory. What is the kind of trajectory of a massive particle? Massive particle does not mean heavy. It means it carries mass. Okay. So now tell me, if I am having a massive particle, how I write the geodesic of the massive particle? So what is the geodesic of a massive particle? Geodesic is time-like. Clear? So what is the definition of our time-like event is? ds square is less than 0. Samajh? So in other words, we will write in, since here we are dealing with the velocity vector. Okay, the tangent to the curve that describes the trajectory of the particle. Okay, so we have to write now the equation, the time-like condition in terms of the velocity of the particle, because we are dealing here with the vectors. Okay, Samajh? So how I will do? So let me tell you how to do. So you are having this very as the line element, g mu nu dx mu dx nu. Samajh? So if I put it less than 0, can I write it? So what does this mean? This object is what? ds square is g mu nu like this. You sure? Sure? Okay, so can I write it like this thing? G mu nu dx mu by d sigma dx nu by d sigma less than 0. Can I write it? Can I write it? It is simply the differentiation. Forget about this thing. So it is simply the differentiation with respect to what? Sigma. Or in other words, you divide it by sigma, it is less than 0 still. Clear? Got it? So what it gives me? So it gives me g mu nu x dot mu. So this is x dot nu, that is less than 0. Samajh aaya? So it means our condition is g mu nu x dot nu less than 0. Clear? Samajh aaya? I can write it like this thing. So what is the natural constant at hand in terms of the velocities? Velocity of light. Is it? C is a natural constant. Can I write it like this thing? G mu nu x dot nu is equal to minus c square, because c square is a positive. If you see, it is a velocity square. Is it? That's why I have put a what? A c square to be dimensionally correct. Okay. So now minus I have put to be less than 0. Samajh aaya? Clear? Okay, good. Now let's expand it. So let's get the condition. What is the time like geodesic? So this very equation will give me the radial equation of the particle. Okay. Look here. So this radial equation is valid for what? Both time like as well as null like geodesic. Clear? But I am now considering only what? Time like geodesic. So I should get actually the radial equation from this very equation. Samajh aaya? So instead of taking this very equation, I should take this equation. Got it? Okay, so let's calculate it. So what it is? So G00, so it will be something 1 minus twice mu by R C square T dot square. Okay, so G00, 00, C T dot and so on. Okay, then you are having 1 minus twice mu by R. Okay, then you are having R dot. So it is R dot square. Clear? So in which plane we are? Theta equal to pi by 2. Okay, so that means sine square, which term will contribute? Only phi term. So I will be having like this. So let me write those terms. So this will be simply r square theta dot square, then we will be having r square sine square theta phi dot square is equal to minus c square. So this term is now not there. Got it? So I should write like this thing now, plus r square phi dot square is equal to minus c square. So let's solve this. 1, 2, 3, 4. Okay. So now let's substitute. What is the value of t dot? So I want to eliminate t dot and phi dot so that I will get the radial equation. So now using value of t dot. So how much is that? So it is k into 1 minus twice mu by r raised power minus 1, and phi dot is how much? So h by r square. So you need to substitute it in this very equation. What we will get? So let me write the equation. It is simple. Substitution. So then I will stop. Okay. So we will be getting like this: r dot square plus h square plus r square 1 minus twice gm by c square r. Okay. Minus twice gm by r. So that's equal to c square e square minus 1. What is gm? So our mu is actually equal to twice g. Okay, rather gm by c square. So this is our radial equation. call this as equation 5. So this describe, okay, so this equation can be used to describe now the free fall of an object in the Schwarzschild space-time. समझ आया? Now if you take r tends to infinity, let's take r tends to infinity, this k will be actually 1. Okay, because at the infinity you are having the simply energy of the particle that we have seen. Interpretation of this k. So this k will be 1, this is equal to 0. So what will happen to this thing? This term goes to 0. समझ आया? So let's keep this term for the time being. Okay, so let's keep this term. So what you get? R dot square is equal to like this thing. It is same as the Newton's equation. If you double differentiate it, it is same as the Newton's equation. R double dot equal to minus gm by r. What we have seen, the free fall of the equation. So let's try to do it tomorrow in the next lecture because it's already late.